Okay, we get going. Yes. Okay, it's a great pleasure for us to have Ryoichi for a brief visit. Yeah, I wish we could stay longer, but anyway, he's going to tell us about direct numerical simulations of active particles in complex environments.
Yeah, thank you very much. Yes, so as kindly introduced me, so I'll be here only for 3 days. And for 1 year ago, actually, including today, today's Saturday, right? No, when today's Saturday, right? Okay, so let me talk about this topic for a while. So, Ryoichi Yamamoto from Kyoto University, and actually, yeah, so I'm visiting Matthew in Warwick University for this week. So this is the middle part of my visit in UK. Okay. So this movie represents what I am doing so far for already 20 years or something. So we in Kyoto University try to develop numerical methods which can be applicable to simulate many particle dispersion in fluid, various kinds of fluids. So you can see striking example here. So here you see, believe it or not, so you see the motions of 10 to 5 number of particles sedimenting down due to gravity in fluid. So such a large scale simulation can be done on normal PC just for 1 day. So that is the strength of our method.
With hyperdynamic?
Yes, of course, yes. So here another example. So the fluid is no more one component, but 2 components, A and B phase, blue and red. Then the particles immersed in that system. So the particles somehow prefer to sit in between red and blue. Therefore, this kind of so-called Pickering immersion type situation can be occur. So this simulation also can be done on normal PC for a few hours with hydrodynamics.
So what's the resolution of hydrodynamics?
Good question. So we use grid. In order to resolve 1 single particle for a diameter, so we use 8 grids, which is quite okay. I can tell you later. Okay, so this is the content of my talk today. So let me first explain very shortly about our DNS method. Just a flavor of that. I don't want to explain full detail of that method. Then I will speak about the corrective motions of modern microstreamers. And then, so I will speak about the corrective motions of Twin-K rollers, that is the artificial type of active particle, which is kind of popular these days. Good thing about this artificial active particle is the reproducibility is much higher than the biological systems. Then a few new directions will be shown using our method. Okay, let me start with the method. So in order to simulate particle in fluid, so the straightforward method is to solve fluid motion using Navier-Stokes here, and particle motion using Euler and Newton-Euler equation, so the translational rotational motion. Of course, these equations cannot be separate with each other, so these have to be coupled to each other. So in the sense of the corrective momentum exchange has to be taken into account. Usually, so if you do that, if we want to do this kind of calculations, the most straightforward method is using the method so-called finite element type simulation, in which we discretize the system into irregular mesh. So in order, if you use this, any kind of shape can be resolved on computer simulation, spherical particle as well. But the problem is the computation is extremely slow. So you can imagine that if one particle moves from this position to another position, then you can remesh all the entire space, then transport information from defined on one mesh configuration to new mesh configuration. It's very, very inefficient. Then this is why in this method, the momentum transport is achieved by surface integral. So the force acting on particle is obtained by integrating the stress acting on what we need. Is very inefficient in that way. So we are not the only one who is doing this. Well, many people are doing this, but so I mean, because this is very inefficient, so naturally we want to simulate this kind of equation using square grid, right? As you can see here. But the problem is here is the spherical object or any orbital shape of object cannot be necessarily fit onto the square grid. You can imagine that some zigzag type of surface can occur. Therefore, in order to avoid that, we introduced diffuse interface. So that is everything we have done for this. All the further details are just a detail. The benefit of using this type of method is, of course, the computational efficiency. The computational speed compared to this, this is at least 2 orders of magnitude faster. You might be interested in the accuracy of the method. I will probably tell you about the accuracy of this method at the end of the talk. Okay, so this is the last part of the method. So started from the configuration, define that at time step n, particle translate, so particle center of position and particle velocity, and the rotational angular velocity of particle, and the fluid velocity, defined at time step n. Started from this, we first update the fluid velocity and the particle position and velocity without considering constraint at all, without considering a momentum exchange at all. Then in the next step, we take into account the momentum we take into account the momentum conservation by some method. Then we finally obtain correct those values at the next time step, for which we take into account the momentum conservation. So repeatedly using this, we can simulate the couple of equations that I showed.
So sorry, could you go back to that? So you first step, you update the velocity field and the position of the particle.
Yes.
Second step, the velocity and angular velocity and angular velocity of the particle.
Yeah.
And then third step, then you do the fluid again.
Exactly.
Okay.
Yes. Yes.
What about the orientation update?
Orientation. So yes, so at this moment we assume particle is spherical. Therefore, I mean it doesn't anything to the orientational.
What can
Then we can resolve that as well. So the orientational configuration can be. So
your stresses, you may still have stresses that will
yes.
the particle,
Yes.
right? So
The hydrodynamic stress. Yeah. So which affect to how to say, so the interface surface of the particle. Then if you integrate, so in a sense, or integrate the stress over the surface, then you will obtain force and torque acting on the particle.
with the diffuse layer, so there can be limitations with respect to anything like lubrication forces or high density systems, presumably.
Yes, of course.
Maybe you'll get into that, I guess.
Yeah, maybe it's already a good time for me to explain that accuracy. So this is the accuracy when we calculate the drag force acting on the array of particles. So if the density is 0, so that so that mobility is the well-known value of Stokes value, right? But with increasing the volume fraction of this array, so the mobility decreases. We know the theoretical prediction for that. This dot corresponds to the numerical data with resolution of 8 grids for one diameter of the particle. As you can see here, so as far as we are interested in the drag coefficient, the accuracy is very satisfactory.
But that's a drag with a single particle. If you have when you have multiple particles.
But here we have, so actually, so we have.
But it's still within. It's still a single particle within many particles. So I guess I'm just sometimes when you get lots of collective particles and you've got implication forces, that can really change the collective behavior.
Exactly. Yeah. So that is right. And then this is the lubrication. Lubrication is a little bit harder for us to achieve the good accuracy, as you can imagine. So because we have a diffuse interface, therefore the distance between two interfaces to particle comes as comparable to the thickness of the diffuse interface. Then our method will use the accuracy. That's a kind of round inaccuracy, I would say. But below under this point, so our method very correctly reproduce the lubrication force acting between two particles, or also for the many particles. Okay. So these are the kind of visualize summary of what we have done or we have used for our method to simulate. Started from so we have developed the code. Then we are releasing the really available code from the internet. So with this name, so if there is anyone who is interested in this code, so you can reach to the entire source code from here. Okay, so this is the method. Then I will show you some results using this method. The first one is about the corrective motions of model microsystems. So corrective motions. So you can imagine that the corrective motion is, typical corrective motion takes place for the flock of bars here, or the school of fish here. Then for flock of bars, we believe that the hydrodynamic interaction between bar and bar is not so important, at least we believe. Therefore, this type of system is called the dry particle system. And for school fish, so that we can believe that the hydrodynamic interaction plays some role. Therefore, this type of system can be called a wet particle system. So I want to distinguish these two. For dry particle, they already developed several good model, started from Bicek model, everyone knows, of course. And then after some treatment, so we can even obtain the container model, which is essentially reproduce the Bicek type of model. It's okay, but it's not our approach. And then another type of popular dry particle model is, of course, the active Brownian particles. And in both cases, the activeness is imposed by the constant velocity applied to the particle pointing toward the polar direction. It's okay, but for wet systems, we can think a little bit different model. So let us learn the physics of swimming here. So this represents how can wet particle propel in fluid. So here is the swimming guy. He does paddle stroke. That means so he push water downward. Then as a counter force to satisfy the momentum conservation. So this guy can propel upward. So this is the mechanism of swimming. Momentum is constant. So that momentum conservation is very important, concept of swimming. But also the same is true for the talk. So this is the schematic model of bacteria. So the bacteria try to rotate its tail in some direction. Then another counter torque, so the body tends to rotate the opposite way. But the total momentum is not that. Total torque is total rotational momentum is constant. So these are kind of conservation is the important concept for microsystem, let's say for the with the particle systems. Swimming means propulsion without external force, external torque. Momentum is conserved. Then the other very apparently difference appears. So if you put a single particle in fluid, and if you externally driven that particle, flow induced around that particle decays only the power to the distance to -1. But in case of this force-free type of propulsion, so the created induced flow decays with R2 power minus 2. There is a big distinction. So the other, I would say that the other micro swimming type of particle have a shorter interaction between among them. Okay. So the other, what is a good method to simulate wet particles? We can think about the other explicit swimmer, something like this. This is the very detailed model for bacteria. You have a body, you have a flagella, you can rotate flagella against the other body. That is possible. And actually, so that one of my friends, Ishikawa-san, did this type of simulations for 2 bodies. That is possible. The problem here is the other, because this is too detailed. So it's not possible to simulate thousands of numbers of such kind of particles that are simultaneous. So we wanted to.
Can I just dispute that?
Yes, yes.
It is possible.
It is possible? Yes.
No.
How?
You can look up our codes. You can look up our codes.
You go.
Yes.
Okay.
We don't have an explicit tag.
We can have it.
Yeah. So the other another simplified model is this squammer. So instead of having explicit shape, so here this squammer particle have a boundary condition. The kind of moving boundary. So the boundary motion can be reproduced by superposition of polynomial expansion in any shape, in any configuration. Usually, we only take into account the other motion in this polar angle direction, because that is most important term in order to achieve propulsion. Okay, so I would say maybe I think most of you are already familiar with this type of thing. So in order to model, for example, bacteria here, so we can reproduce very characteristic flow profile around this bacteria by using 2 contributions. One contribution is the surface moving boundary condition started from North Pole, passing equator and ends in South Pole, the monotonic flow. So if we have this, so fluid around this particle is pushed down, then this particle can propel upward at something similar to the paddle stroke. Then we need one more higher term for which that surface boundary condition, but surface moving boundary is started from North Pole and in equator. Another one is started from South Pole and in equator. So this does not contribute to anything up to the propulsion, because this tends, so the upper hemisphere tends to push particle down, lower hemisphere tends to push particle up. Then the other effect is compensating to each other. But this term is very important in order to resolve, or in order to distinguish pusher or puller character of the microswimers. If this, so the alpha is an important parameter, strength of B2 normalized by P1. When alpha is negative, so the flow around the particle becomes this type of configuration, which we call pusher. And alpha is negative, positive, opposite, polarized is obtained. So if we have this second term, we can distinguish pusher and puller. And then this is a very used model to discuss about this difference between pusher and puller. We will go for a bit more later. Then this is another numerical scheme which we invented, we developed for this type of thing. So the essence is the same. So we update these variables without caring anything. Then we take into account the momentum conservation. Then repeatedly using this, we can simulate this type of microswimmer, the many microswimmers simultaneously. So you see one example here. So this is the externally driven colloidal particle. As I told you, so the fluid induced around this particle decays very slowly, R2 minus power of 1. This is a neutral swimmer. So in this case, so the decay takes place much quicker. So the decay with R2 minus 3 in this case. Then these are three different cases for neutral case center, pusher here, puller here. Then
So in these simulations, your slip layer is, you use that to be the same size as your diffuse layer. So your diffuse layer is a slip layer, you have a different scale for the slip layer. The same scale.
So that's another boring up to now. So the other, comparing to the other neutral case, pusher or puller, the fluid velocity decays with the power of -2. But this is recorded. Up to here, you may think that pusher or puller is not so much different. As we are looking at the single particle motion, those two pusher puller, it looks almost the same. But the situation is completely different if we look at the collective motions of such microsignals. You will see this. This is a result obtained by Abunabala's group already 10 years ago. So what they done is they put many of pusher or puller or neutral microsigma together in a periodic boundary box with volume fraction of 10%. Then if particle is neutral, such a particle have a strong tendency to swim into the same direction. Therefore, if they calculate the polar order parameter, it very easily becomes to 1. Everything seems together in the same direction. But as the pusherness or pullerness is increased, so such a preferred polar state is destroyed. So such a destroyed polar state is much easier in the pusher direction than in, puller direction than in pusher direction than in puller direction. There is such a big asymmetry. The origin of this asymmetry is not yet fully understood. Not only this, maybe another, so this is the same system to the previous one. We confined many of pusher particles and puller particles in a parallel plate. The confine. Then you can see what happens. The difference is only this one is pusher, this one is puller, the other one is puller. So for pusher, nothing really happens. The microsigma tends to collide in a kind of random manner from beginning to the end. But for puller, as you see here, the density fluctuation spontaneously takes place. Then the dense cluster of microsigma tends to propagate toward from center to upper plate, then bounce back, then bounce back. This kind of repeated motion spontaneously occur.
So this is not periodic boundary conditions. This is fixed,
Yes.
non-penetrating. Yeah.
So please remember that the difference between this and this is only either particle is pusher or puller.
Would you get a propagating wave in the case of periodic?
Yes.
Yeah.
We can calculate. We can obtain the relation between wave number and so the next one is the same plot, but to see the result more easy manner. So we plotted the density of microsigma in this green code as a function of time. For pusher, nothing happens, but for puller, as you see here, started from random compilation, spontaneously density wave appears, and then it propagates, bounce back, propagate, bounce back. It continues forever. So
is there any, do you explore size dependence? What happens if you vary the box?
So if we increase the size, then the slope doesn't change. This just goes to this and this. And then if the distance between these two plates are so large, then you may have multiple waves. So that is that. But the interaction between waves and waves are almost not. It's like solid on time.
So just what happens if you have the walls flexible?
Sorry,
What flexible one?
Flexible wall. Actually, I don't. I cannot answer that. Which okay. So the other from I mean, this is the most exciting result so far we have obtained for the multiple corrective motion of microschema. And then also quite interestingly, so such a propagating wave phenomena takes place in a very narrow region of value of alpha, at which this asymmetry exists. If the value of alpha is out of this asymmetrical behavior region, so the nothing happens. And more interestingly, so we tried to reproduce this behavior, this asymmetric behavior by using binary collision model. So because we use DNS, we can do anything. So we took the two particle, we simulate two particle, started from one, the one configuration. Then we observe collision between these two particles. Then it collides and depart, something like this. So from this experiment or numerical simulation, we can obtain collision rule for this configuration. We change it the initial configuration very many. Then we constructed overall collision rule for specific value of alpha. Then we tried to use that collision rule, it's a kind of map, to reproduce the final state, which is plotted here as a red dot. So as you see here, so no asymmetry appear. That means the answer to this answer to explain the origin of asymmetrical behavior between push and pull does not exist in the collision of two particles. It's apparently some many body effect. That is I can be sure. But still, we do not know clearly answer what is the origin.
That's known to be true for non-hydrodynamic flocking as well. You can't get flocking without three-body interaction. In the non-hydrodynamic versions, like if you want to coarse grain something to get turner 2, you have to have three-body turns in the microscope.
Okay. Yes.
Can I just clarify what the boundary condition is on the particle when it hits the hard boundary?
So we just how to say, so we just place the plane plate.
Yeah.
So so there is a hydrodynamic interaction between plane plate and particle.
Yeah.
That's all.
And when it actually touches the wall, what happens?
Yes. So what do you mean? So if we very accurately calculate the relocation force, the touch does not take place.
Yes, but the finite grid.
Yes. Therefore, we introduce the how to say excluded volume interaction in order to
Some finite range.
Yes.
And does it affect the rotation?
It affects rotation because so we have a moving boundary. Therefore, depending on the orientation of the particle, so the particle tends to be rotated this way or this way.
By the hydrodynamics,
yes,
and not by the whole particle interaction. And that's an obvious second source of
yes,
difference between two particle situation and
yes. So that right. So we still cannot completely neglect the possibility of the whole particle interaction based on. Okay, then goes to the next system, Quinquet rollers. So Quinquet system is this. So we place dielectric particle between two electrolytes, which is fluid with some fluid. Then as the electric field goes large, this particle at some point starts to spontaneously rotate. But the direction of rotation is in. So this is the very interesting system for the Quinquet rollers. So the experimental plotted here. So here we see the motion of such a Quinquet rollers from top. And the particle roll straightly until it collides with something. but yeah, that direction can be anywhere. So this is the other system. And then they are already have done many experimental and numerical studies on this, I would say. And then this is experimental data. So with changing the area fraction of the system and also the intensity of the external electric field. So people observed many distinct dynamical states, from gas state to polar state, rotating cluster, the crystal, those kinds. So they explained it. Okay, and then there is a theory for that. It's a simplified theory, of course. So the actual system is 3D. In 3D of domain, the particles rolling. But yeah, this model is two-dimensional projected model. So here we have a collisional particle observed from within the plate. Then the rotation, this rotation is not the rolling rotation, direction of the particle. Then so that they can construct a model. And in which they take into account, it's a very complicated model. So it's difficult to tell me what part of interaction is included, what type is not included. But this is my final understanding. So they included the far field hydrodynamics. And they also include the short range hydrodynamics effectively, and electric interactions as well. It looks like they included everything, but it is not. So this is a similar model. It's almost identical model, and they did numerical simulations using that model. And they say they reproduced experimental observations quite well. But I had an impression that something is still missing if we compare the full 3D system and this system. That is why we did full 3D dynamical numerical simulation for this system. So we do simulation in 3D. So we placed many rolling particle on the plate, solid plate, in the sea of fluid with some viscosity. Then because of this rolling motion, so the flow is created around this particle. And if we compare our result with the much higher other people's numerical data, which is obtained by much more extensive method, maybe, I don't know, 10 to 3 times more extensive calculations. And then the agreement is very nice, very good, again. And then so their problem is they can use this kind of method only for a single particle. But we can use this method for any particle system. Of course, accuracy is, this one is much higher. But anyway.
So what happens at the fluid underneath the particle?
This one?
There, yes.
So the hydrodynamic boundary condition on the plate is zero velocity. Then the particle is rolling. So therefore, there is a tangential lubrication force. It's difficult to say. So the gap between particle and plate is non-zero. So there is some non-zero thickness, and depending on the thickness, the rolling. If the rolling angular velocity is the same, so the particle translation velocity is different. There is theory for that, and we quite correctly reproduce that. Yes.
Yes. Also in the experiments, they find that when you have little microscopic roughness on the surface,
yes,
and this also affects what happens. So yeah.
So I have a very naive question. So which is so if I think of this particle which is spinning there,
yeah,
then I can probably, if there's in near a wall, then there's an image particle which is probably spinning. And then if I can think of these as sort of resolve it with a non-zero like magnetic moment, so then I could think of the interaction between these two. And that probably, if I have to balance the stresses at the boundary, and probably leads to some kind of a clear flow between the object and its image. I don't know whether for not from this field, so I don't know whether for swim pushers and pushers, that makes the difference.
I cannot fully answer to this question, but I mean, so the similar condition can be achieved by, as you told me, so if we use the mirror image of this particle underneath, then without having plate, so the completely the same boundary condition can be realized. But maybe from theoretical point of view, that type of system is much easier than introducing the plate. But we have numerical simulation, so it's not a problem for us to introduce plate. Therefore, we use this approach.
So
But the image is complicated. It's not just
you
need more than
this
you need more than just one image. You need actually other so actually it's quite complicated to use images.
I have a question about the noise. So if you can back up, if you back up, the noise that has been added here, which raises a question for me also about simulations. So if you're going to take into account hydrodynamic interactions between the particles, now I understand with the Quincke rollers, they're against the plate, so maybe you can ignore the hydrodynamics. But to the extent that you do need hydrodynamics, you also need to take into account correlated noise. So it looks like the noise is independent Brownian force.
That's right. Yeah. So I don't think they introduced the consistent noise, which can, I mean, what to say. So we have to satisfy the practice in displacement type of relation.
But this is not a grouping system, so it doesn't have to satisfy the complexity.
Except that it does, because we know where that
Sorry?
we know where the noise comes from.
Well, I mean, we know some of where the noise comes from. We don't know
You know, at
anything.
least part of it is not. Okay, so this is explicitly in an active limit in which Brownian is gone.
Yeah.
But back to your simulation method,
We
though.
neglected the noise. This is why maybe there needs some discussion on that point of view. But I mean, for many microsima systems, thermal noise is not so important.
Okay.
I mean, so the noise due to the collision is more important. That is my understanding.
Okay, but if you were to use your
Yes.
so back to your basic approach, your simulation approach. If you do this for a colloidal suspension without active forces, does that include correlated noise consistent with fluctuation dissipation?
Yeah, I mean, I have to confess that. So we can add noise here, here or here. So if we add noise into the Navier-Stokes equation, then we can construct consistent formulation. So for at least for the non-active systems. So I mean, fluctuating hydrodynamic is already well established.
Exactly.
We can use that approach.
So that is in this whatever capsule, whatever.
Yes.
Package. Okay.
But there is a technical problem. So the fluid is resolved in a grid, which is much smaller than the particle. Therefore, if we introduce noise into the fluid, then time step have to be very tiny, which is unnecessarily tiny to resolve motion of particle. Therefore, we very, empirically add noise to this equation. Therefore, we can say that we introduce noise here, but definitely, so we do not satisfy fluctuating dissipation at all. If we want to satisfy fluctuating dissipation, we need to add phosphate. Okay, sorry. I'm going to go to the then. So this is the summary of the computer simulation from our method. Very similar to the similar presentation to the experiment or the other people simulation, area fraction and the intensity of external field. And then we observe many kinds of differentiable dynamical state. And then it's only from I, but we distinguish all these states into 6 categories, 6 phases. Polar liquid gas, vortex, chain, blah, blah, blah. And the representative state from each 6 states are here. So the polar state, everything is rotating in the same direction. Gas state is something like a gas. Effective state is there is a domain in which particles are moving coherently, but there is a finite size for that. The chain is quite interesting. So no one yet from computer simulation obtained this, something like this. The rotating state, this is also not, I think we are the first guy who succeeded to reproduce rotating state from computer simulation. It's already obtained. So this is the result. We do 3D, yes.
So for your change state, in which direction are the individual particles moving?
So the color represents the direction of rotation. Therefore, when this chain is moving in one direction, all the particles rolling in the same direction.
But so they would be they're slipping with respect to each other and what's in
Yes,
different.
yes, that's important. I skipped that part because of time. So the other, on top of the hydrodynamic interaction, a particle have a dipole-dipole interaction. Because we apply electric field, therefore the induced dipole is induced. Then the other particle tend to rotate in this manner when the electric field is strong. So that is that.
So actually, what you are solving, are you solving the E field interaction with the fluid directly?
Yes.
Okay, so and
sorry, so the other E field, so the other.
because it's a charged fluid, so you have counter ions in the fluid and such. So how are you dealing with?
I'm sorry. So the other, we do not resolve the other formation of induced dipole from first principle. So we use some theoretical simplified prediction of the other induced dipole as a function of external field.
Okay. So you just put dipoles on the particles and you see how to interact by these dipoles.
Yes.
Okay.
Okay. So the last one. This is the other. I will finish this within 5 minutes. Okay. So the other. Now we are quite confident going towards the other complex fluid, and then several new approaches has been started. Now I want to speak about this. So the other microsima discovery. This is actually the other what one of my students, Kobayashi, who will visit here from this September for the month, is doing. So now the fluid is viscosity. So we use very simple ordered V-type fluid, which is viscosity. But they are very simple. It's a Maxwell model with upper convection. So this is the model. Then on top of the 2 terms, we added another so-called Lotlet term, a simul-small surface motion of the dipole type. This. Then the other strength of this term is normalized by strength of this. So zeta is a new important parameter. As zeta becomes large, the twisting motion becomes large. So this is the other people's data. The Professor Sakufed's group from. So they simulated the type of scalar particle with Lotlet in the cylinder. Then they observed propelling speed of such a particle as a function of Weisenberg number. Say that the degree of viscoelasticness. When the Weisenberg number is considerably large, they observed that theta equals 0, no twisting. The velocity is almost similar to the other Newtonian case. But as the twisting becomes large, then they observe the considerable speed up of the particle. So What is this? I want to answer this. We do the same calculations using our method. But here, the presentation is the speed up. But 1.0 Newtonian case, the speed up of the 8% or something is a little but as a function of twisting intensity. This is a Newtonian case. In case of Newtonian, even if you twist very rapidly, so nothing happens to the propelling velocity. But if the fluid is viscoelastic, then speed up takes place. Okay. And then the data is very consistent with the surface data. So we are quite confident that we can answer to this question.
When you say nothing happens,
yeah,
is that kind of numerically nothing, or is it just very small?
Probably very small because the other.
But I don't think there's a symmetry or anything, which means that
yes,
you can't do anything in Newtonian.
So the other in a Newtonian case, in Newtonian fluid, we do not have any normal stress difference. And this is due to the normal stress difference, as I explained in the next slide. Therefore, this is really nothing. Okay, the mechanism is very simple if we understand the truth. So, I mean, if we put twisting boundary condition particle in cylinder without D1 term, so I mean, this is rotated. Then the method which you do well known as the Weisenberg effect. So the normal stress difference takes place around the rotating sphere, hemisphere. That effect is stronger at the other somewhere in between North Pole and the equator. Then the other this happens symmetrical to North Hemisphere and South Hemisphere. This is this. Then the other this Weisenberg effect is something similar to the other lava band. If you have particle here, the lava band is trying to shrink in the North Hemisphere and South Hemisphere. Right. Then the other, so this shrinking lava band tends to push down the particle. This shrinking lava band tends to push up the particle. But the other, because of the symmetry, so nothing happens in this case. But if we apply V1 term, the propelling term, then that symmetry is broken. As a result, Weisenberg effect happening in North Hemisphere is weaker than that in South Hemisphere. Therefore, particle is pushed up. This is the origin of speed up, nothing more. So, the last one. We can think about how to propel in a viscoelastic medium. Usual propeller is something like this. It has a chiral shape. If you twist this clockwise, then this can create translational force. That's the usual in our world. But in viscoelastic world, we don't need this. Shape asymmetry alone is enough. So if you have this cone-like object, then rotate, not necessarily rotate it in one direction. This kind of reciprocal rotation is also okay. This shape asymmetry can create translational force due to normal stress difference. That is the other. So thank you very much. And also thanks for the Prof. Yeah.
Any questions, comments?
So you showed us that the pullers create this co-aligned system at high density. And just following up on the question about the importance of different n-body terms.
Yes.
Can you get something from looking at scattering interactions, n-body scattering interactions in this context? I know that's not quite the same thing as high volume fraction, but if you look at the trajectories following scattering events.
You mean the corrective motion microsigma?
Yeah. So if you take 2 or 3 or 4 particles and you put them on a gliding trajectory, and so you look at the distribution of orientations as they come out of those collisions. This should give you a hint at how the alignment is emerging, not how you imagine.
Yeah, but are you? I mean, are you saying that the other we can do similar we can obtain similar collision rule for 3-body systems. I think that.
I see. Okay. Yeah, or you could just, I mean, set up a simulation which only have 2 or 3 or 4 particles.
Yeah.
And examine that.
Yeah, it is possible, but the other, I mean, so then we have too many degree of freedom to explore numerically. So it can be done because only we have 2 particles. Therefore, the other, I mean, we can construct a collision map by changing the other mutual angles, also something. But the other, if we have more than 3 particles, then initial configuration, the choice of initial configuration has to be, I mean, almost impossible to do.
At the risk of opening a can of worms, there was some debate about, you know, about how these methods scale compared to other methods. Could you say, I mean, say something about
Numerical efficiency.
yes, numerical efficiency of these models?
So I mean, as far as I know, so there are 3 different approaches to do similar calculation. One is something like ours. So Navier equation for hydrogen. The other 2 is the other, I think that is more popular in Europe. So the lattice Boltzmann can do the same. I would say the efficiency is the same. So the other both have good and bad points. Good point of us is that we can satisfy incompressible condition very precisely, which is not so easy as far as I know by lattice Boltzmann. The another is the other as Professor Compass group 2. Stochastic collision dynamics is also possible. There also stochastic collision has a problem. I mean, I would say it's a problem, but the other, again, the other incompressible condition is not precisely satisfied.
You have to check the sound state always important. Yes.
But that is not here. Therefore, we say we can use 10 times larger time increment compared to those systems. But the other solving Navier-Stokes takes more than much more expensive than just solving. I mean, that's Boltzmann or the stochastic collision. Therefore, I think that really can generate complexity to each other.
What about you based on Stokes?
Stokes.
Stokes you have inertia in your.
Yes, I have inertia. Yeah.
But do you ever need it for any of the problems you talked about?
Okay. So the other, we have inertia, but the other, therefore, I mean, as maybe you see in the very first part, so the other, we can go for the other high Reynolds number case up to 1,000 or something, but it is, I mean, it's main purpose. We usually want to do small Reynolds number system calculations. But yeah, we cannot neglect. We can. It's not. So we cannot remove this inertia.
But it's similar to last Boltzmann in that way. Although in that case, it's because it's partly compressible and you need to propagate these sound waves. But there are methods for dealing with systems without any inertia from the beginning.
Oh yeah.
And Stokes, I'm not aware of how that would scale, but is yours based on Stokes?
Well, it's based on removing the fluid. So you turn the Stokes equation into an integral equation, and therefore the integral equation is solved only on the particle boundaries, and the internal fluid is completely removed. So that scales quadratically with the number of particles rather than the volume. Whereas with any grid method, if you have a fixed number of particles, you increase the volume of the box, of course, the computational cost is going to scale.
So the other, I mean, the one apparent merit of DNS, including Boltzmann stochastic annotation, is the other applicability for complex fluid is very wide. So the other, I mean, we can add another, I mean, some complex degree of freedom to the fluid. So that, so if, I mean, so the other, we can do the same thing, for example, using the other Stokesian method. So the other, because we know the other hydrodynamic interaction between the spherical particle. That is okay, but it is only okay for the other Newtonian at the zero Reynolds number. If you want to go to the other complex fluid, like two-phase fluid, two-phase mixture or the viscoelastic media, then the other we have to considerably change the structure of solution.
Well, if you have an incompressible viscoelastic fluid, you could still do an analog of what would be written Prager, Yamamoto, or Osi. But it's probably very inefficient.
Yeah. But I mean, I guess the issue, you would claim would be that you, at least when the particles get close together, you do better than Rotner, Prager, or Yamamoto type approximations. That would be argument. I guess and of course you can look at maybe a couple of other fields to the dynamics. I've got another question which was related to the noise and fluctuations.
Yes.
In most of the simulations that you showed, you basically you ignored it. You basically didn't have noise. So do you have any idea of what happens if you add a little bit of noise to some of the behavior that you showed? For example, like this when you had a boundary and this.
I think as far as we are interested in active systems, the effect of noise is minor. I don't know. I can convince you or not, but the activeness is much larger than the randomness.
But zero randomness is not the same as very small randomness.
Okay.
Well, it's getting very chaotic. Once you've got self-propulsion, the argument would be that it's sufficiently chaotic that if you come along and add a little bit of noise to that, there's nothing really changed.
But it's presumably starting, that depends on initial conditions as well. It's those things that, I mean, your initial condition somehow, you're somehow saying there's some noise in initial condition, but this is what grows with time. So I guess.
And that really, I mean, if you think of Stokesian reversibility is structurally completely unstable. So particularly at high density, the noise you need in your initial condition is really infinitesimal. It would only be if you, with numerical infinite accuracy, put things on a regular lattice or something that it wouldn't go chaotic after a while, I think.
Yeah, probably.
I mean, just before closing my talk, I want to show one movie, which is obtained very recently. So this is the application of method to catalytic microsimulation. Catalytic microsimulation, maybe this kind of thing. So the name of the genus particle. One side is catalytically, chemically active. The other side is chemically inactive. Then some chemical reaction takes place on the one side of the hemisphere, which can drive the particle. And we implemented the numerical model for that. And then introduced chemical reaction on the one side of the hemisphere, the other side of the hemisphere, the rate of chemical reaction is 0. The model is this. This is the other chemical reaction term. This term is just needed to conserve the total amount of chemical concentration. So, I mean.
So, but in reality, the fuel is being used up. So the fuel is being used up.
Yes.
So it's
we put fuel.
Yeah.
I mean, uniformly to the system. So that is that. Then the other, if you know, there happened a big discussion on this kind of system using PRLs. So whether or not osmotic pressure can drive the system, of course not. So if you don't have this term, so this term represents the chemical affinity of the particle with the some component of system. Without this, we can still have chemical reaction. We can have an imbalance of osmotic pressure from one side to the other side. But that osmotic pressure imbalance has to be completely cancelled by incompressible condition, the pressure, hydrodynamic pressure. Therefore, if you don't have this, although we have this chemical reaction isotropy, particle does not move at all. With this chemical affinity term, owing to this chemical affinity term, our particles can very slowly at the other move toward the high density region of the hydrogen peroxide. So I'm quite satisfied with this model so far. So that is the end of the presentation.
Okay, so I mean, Ryoichi's around for, I think, another couple of days, so I guess if we want to chat with him, just,
Yes, I'm happy to do so.
so